Okay, so let's take a look at that. So I'm considering an array of two RX antenna. This would be this guy and this guy, with separation D between them. I'm considering rich multipath, yeah? And for simplicity, because I don't want to carry all the e to the minus j 2 pi f tau with me, I'm just doing the evaluation over the carrier frequency, but this is not limiting. Of course, I can do it anywhere, and the result would be the same just for simplicity. So what would be, in this case, the channel, again, rich multipath, respective to the first antenna element? It would simply be identical to SISO. It would simply be sum of AI. And again, AI in this case, everything is baseband, so these guys include both the gain, of course, and the phase. Okay. What would be the channel, and this is the key point, associated with a second antenna? So it would be some AI, but each one of them will have an additional phase that depends on the direction of arrival of the specific path. So I'm interested in the correlation between the two, the channels associated with the two antenna elements. Again, I remind you, this guy is identical to SISO. Essentially, also, this guy is identical to SISO. So we already know that multipath would result in the assumption that each one of them is complex normal. We already know, and they would have identical power because it's totally symmetric. But I want to also show to you that I can find a separation to make them IID, to make them decorrelated. Okay, so let's play with it a little bit. This derivation is very similar to the derivation of the Jake's PSD that I've done in the previous lecture, so I think it will be quite easy for you guys to follow it. So I want to compute the expectation of H0 times H1 conj. So I replaced the dummy variable here with a k to avoid contamination with the dummy variable I, and of course also conjugation here and also conjugation here. So first thing, again, very similar to what we've done in the Jake's PSD proof. Of course, EAI-AK conj equals 0, because they are, of course, the AIs are IID. So actually, all the cross terms in this expectation are totally nulled out. So again, like the Jakes, we are left with the sum of the AIs by themselves, where the same index is on the two sums. So of course, I can move the expectation here, because the expectation is a linear operation. So I understand that actually this correlation would be a constant multiplied by the expectation of e to the j2 pi d sine theta over lambda, where this expectation is over theta. Actually, the only random variable that we have here. So it's rich multipath, and we assume that the direction of arrival is actually uniform 0 to pi. So this should be a relatively easy integral to evaluate. We need to integrate with respect to the density of theta. So it would be 1 over 2 pi, again, uniform distribution, 0 to pi, limits from 0 to 2 pi, e to the j 2 pi d over lambda sine theta d theta. Okay. Yeah. What we see here actually, if I gather 2 pi d over lambda together, and I denote it X, what I actually get is the definition. This is the definition of the zero-order Bessel function at the point X. This is the definition. If you look like, for example, Wikipedia for zero-order Bessel function, you will find, alongside with other definitions, because Bessel function has multiple definitions, you will find this definition. So essentially, the expectation that we're looking for, like the correlation, acts like a Bessel function, zero-order Bessel function. This is the red guy here, the zero-order, the red guy here. And the argument X is 2 pi d over lambda. And we're looking for zero correlation, okay? We're looking for zero correlation. The root of the Bessel function, the first root, you can see we have multipath, is at 2.4. It's approximately half of the 5. So the first null or first root is at x equals 2.4. But again, our x is 2 pi d over lambda, so we want 2 pi d over lambda to be equal to 2.4. In other words, d is 0.38 lambda. This is a result, I can tell you, this is the result known mostly to professionals. Yeah, if you would ask even antenna experts, what would be the separation required for minimal decorrelation, most of them will tell you half lambda. This is the result of like a professional result, yeah? The pros in the game know this 0.38 lambda, know it very well. So actually the spacing that we want in order to totally eliminate correlation is not half lambda, it's 0.38 lambda, but you can see that if I increase it just a little bit and I move to around 0.5 and still get quite low correlation. So half lambda, which I remind you, we got half lambda from a totally different consideration. The half lambda was like from the spatial Nyquist. Half lambda was obtained as a classical result from a different consideration. What would be the spacing that would allow me to reconstruct my signal along the array in full, but actually from a totally different perspective. If I'm taking a look at what would be the inter-element separation that would lead to minimal correlation, actually to zero correlation, this is a similar result, 0.38 lambda. But we see that essentially if we have antennas that are separated around 0.5, 0.38, something of this nature, then we can achieve both very good decorrelation and also full reconstruction of the signal. Again, this is like a professional result, yeah?